Hello, and welcome to Remcom's webinar on circuit element optimization. I am Jeff Barney, a product marketing manager, and I will be walking you through this introduction. The circuit element optimizer was primarily developed for matching network design, and this technique is unique to Remcom, so you will only find this module available with XFdtd, which is our 3D electromagnetic simulator. Today, I will start out by explaining what the feature is, then talk about how it differs from other approaches that try to do the same thing. Next, I'll discuss the antenna design workflow and show parts of the user interface. And finally, I'll spend a couple of minutes on some of the more advanced capabilities that are available for tunable components. At the end, there will be time for questions, and you can actually ask questions at any point in time. My colleague Scott Langdon is here, and he can answer questions as the webinar is in progress. I'm expecting roughly 25 minutes for the demonstration portion, and then an additional 5 or 10 minutes at the end for questions. The circuit element optimizer determines optimal circuit element values for a given PCB layout. And when I say a given PCB layout, I mean consider an antenna that's printed on a multi-layer PCB. You have the ground planes to substrate the antenna, but you also have all the little copper traces that comprise the matching network. And so what the circuit element optimizer does is it determines what the values for the inductors or the capacitors should be given all of the copper traces in the matching network in the antenna. When it does that optimization, it considers the S parameters or system irradiation efficiency, and so you can optimize on either one of those goals. And the thing that makes this module so unique and powerful is that it accounts for the full wave interactions affecting the circuit elements. So since it takes the full PCB layout, it accounts for all of the coupling between the matching network and the components, but then also the matching network in the antenna or any other kind of coupling that happens in that area. So how it works is that you first set up your FDTD project just like you would if you were running a simulation. So you would define the geometry, the materials, the grid, the waveform, everything in your XF project needs to be defined. Once you do that, instead of creating an FDTD simulation like you're used to, you're going to be creating a response matrix simulation. And what this is going to do is it's going to characterize the system. So it's going to figure out what all of the coupling is between the matching network and the antenna, and it's going to figure out the sensitivity for each of the components given the geometry and the environment around it. Once that response matrix simulation is completed, well then you're going to run a circuit optimization. And this is where you take the system characterization and then you but you provide as inputs the allowable component values and then the goals that you're interested in. The optimization will then run and it'll tell you what the optimal circuit values, the circuit element values should be. So let's just look at an example here of an LTE antenna. We can see the antenna is in the corner of the PCB. It's connected down through a transmission line into the matching network, and the matching network is grounded into that darker green ground plane behind it. There's 8 elements in this matching network, and if we take a closer view, we can see that the voltage source or the input is on the right hand side, and then there's various inductors or capacitors that are connected in series or parallel that match the antenna. And so circuit element optimization is going to determine what those values are for the 4 inductors and the 4 capacitors given this PCB layout. So as I mentioned, CEO has the ability to optimize on efficiency. So here we set goals for 5 different bands, and there were different frequency ranges for uplink and downlink operations. So there's actually 10 bands in here. The graph is just the output from CEO and what the efficiency would be given the optimized component values. When selecting those optimal component values, it considers the full wave interactions affecting the matching network. And so this image here is just the field distribution for the active antenna we can see that the antenna is active, and the green and red is showing stronger field distributions. And so we can see the effects on the matching network and the coupling through the ground plane, and all of these interactions are accounted for whenever determining the optimal circuit values. So this is really where the uniqueness of this feature comes in, and really the benefit that it provides. So if we then look at other alternative methods, you may be thinking to yourself, well, I can already do this with the tools that I have available. So I want to go over 2 examples of alternative methods and discuss how they relate to CEO. So the first method is going to be using a circuit solver to design your matching network. And this is based on transmission line theory and other analytic approaches that are used to determine the match based on the antenna's impedance. So you would run a simulation or take a measurement, you would get the impedance of the antenna, and then you would plug it into a circuit solver and determine what that matching network would be. So some of the drawbacks from that approach is that it does not consider the layout. So if you consider the schematic in the top right, it can be laid out in the first image or the second image, and those 2 images are of the same schematic, they're just laid out differently. So in the bottom left, where the voltage source and the first inductor and first capacitor are, they're just connected to the ground plane differently, and there's actually a slightly different ground plane. So from the schematic or from the circuit solver, this would all be treated as the same case, and you would get the same element values out of it. Additionally, the circuit solver doesn't account for a common ground. It assumes a common ground. So you can see in the schematic everything's connected, but in the bottom, the ground may be variable, or you can't really consider it as an ideal common ground across all of the grounding components. And finally, the circuit solver treats the antenna just simply as an impedance block. So it doesn't account for any of the interactions between the antenna and the matching network. It just looks at what is the reflection that you get based on the impedance or the S parameters at its port. Circuit element optimization, on the other hand, does account for the layout. So it will give you different component values that are optimal given the difference in layouts that you've defined. It also doesn't assume an ideal ground, so it will take those 5 different feeding points and just treat them as they physically are, and doesn't actually tie them to a common ground. And then again, it does account for all the coupling. So that colorful image that we saw 2 slides ago shows that it accounts for any kind of coupling between the active antenna and the matching network. A second alternative is you can say, well, I have my full wave solver. I know what all of the components are. I know what the ranges of those components can be. And so I'm just going to create my own optimization. And so I'm going to do that by picking a set of component values, plugging them into the full wave solver, running a simulation, and then looking at results. And based on those results, I'm going to select a second set of component values, run the simulation, and you can iterate through that, putting some sort of optimization algorithm around that loop and selecting the optimal components that you would like. The biggest difference here is that the optimization on the left has the XFdtd, or the full wave simulation, built into the loop. The circuit element optimizer, on the other hand, does the full wave simulation prior to doing the optimization. So the response matrix is where we simulate the XFdtd. Once we have that system characterization, then we plug it into the circuit optimizer and run the optimization. So if you just consider the runtime associated with it, if let's say 10 minutes per simulation, which is fairly quick, you can get through 60 different combinations in about 10 hours. For circuit element optimization, or for the LTE example, there were 8 elements. It took about 2 hours to do the response matrix and the system characterization, and then once we had that, it was an additional 15 minutes to do the optimization. And that 15 minutes accounted for 10 or hundreds of thousands of different combinations in order to select the correct value, or the optimal value. So those were 2 alternative methods. And so now I want to go into just what is the workflow for using this for antenna design, but also within XF. So let's start out with the antenna design workflow. It starts with actually determining the shape and structure of your antenna, just designing the antenna. Once you have that, you're going to want to characterize the antenna so you can run a simulation or take measurements. And what you're trying to do is get the impedance. Once you have that impedance, you can then plug it into a circuit solver in step 3 here, and this will allow you to determine what your matching network would look like. Once you have that, you then actually build it out. So you go back into your layout tool, you build in all of the copper traces, and you plug in the components. And so you actually lay out the matching network topology on the PCB. Once you have that, then you're going to have to go in and determine what those final component values are. So if you're in a lab, you'll be soldering components in and out, taking measurements, and trying to find the component value that fits best. And this is the step in the workflow where circuit element optimization plugs in. So it's this final step where everything is laid out, and you're trying to determine what those final circuit component values should be. So that's where it fits in the workflow. And from XF's perspective, I just want to demonstrate this using a GPS Bluetooth antenna. So here it's slightly more simplified. It's just a 3-element matching network. And the matching network has the voltage source, 2 inductors, and 1 capacitor. When we look at this in XF, we can see that the matching network is laid out. The vias are grounding it to the ground plane in the back. And if I zoom out, we can see the antenna, which is located here in the corner of the PCB. In terms of the geometry, the antenna is laid out or is included as part of the CAD model. The matching network is also included as part of the CAD model, and then the substrate and the ground plane are there. If we look at all of the individual circuit components, they're also included in the project. So here's our feed, and then the 2 inductors and the capacitor are also connected. And, these components do have a value associated with them right now, but the circuit element optimization is going to determine new values or optimal values given the geometry and the environment around it. So once we have all of this defined, along with the material definitions and the grid and the waveform, we're going to come in and create a simulation. So here in the drop-down, there's the XFdtd simulation, which is what you would run just to get the results for a single set of values. But what we're going to want to do is create this response matrix. So this response matrix simulation is where we are able to come in and define the ports or the feeds that we want to optimize over. So here, all of these values we want to optimize, and so we're going to include them. If we didn't include them, well, then they would just use the values that were defined in the project. And then if we wanted to optimize on efficiency, we would come in and define the specific frequencies that we want to optimize on. I'm only looking at S parameters in this example, so I'm not going to check this box. And then the termination criteria is since we are running XFdtd simulations, this is just when the simulations stop, at what level of convergence. So once you add it, it'll be added here to the simulation window, and this will run on your GPUs or on your cluster or your job scheduler or whatever it is that you have set up for running XFdtd simulations. I've already went ahead and pre-run this because it does take some time. Once the response matrix has completed, well, then we're going to come in and create a circuit optimization. And here we are going to specify the response matrix that's associated with it. There could be multiple response matrices depending on different physical configurations, which I'll talk about later. There could also be different operating modes, but here we just have an active antenna, so it's always active. There's not a transmit or receive. And then the goals is where we want to come in and define what we want to optimize on. So we have 2 goals that we're interested in, one for the GPS band and then one for the Bluetooth band. Those bands are built into the application, but as a user you need to go in and define the threshold that's associated with it. So here we have a -4 dB threshold for the GPS band and a -10 dB threshold for the Bluetooth band. We also need to define the components and what the allowable component values should be. So here they're all just treated as ideal components with continuous range between 0.1 or 100 nanohenries or picofarads. So the optimizer will take this as inputs and determine which values within that range it should select. And then the optimizer settings are just letting it know how many iterations to run and how many different permutations to consider. So I can go ahead and create this, and this is then going to run on my local machine. And as it's running, I have the ability to come in and look at the results. So here is the circuit optimization simulation, and we can come in and look at the S parameters. So if I double click on this, it will load the values that are being optimized. So here the optimization is running, and this is the match that we'd be getting in the GPS band, and then the match that we're looking at in the Bluetooth band. The other thing to look at is the actual component values. So here we're looking at the different two inductors and the capacitor that are associated with these values, with these placements, and then we can determine what those values are, or what the optimal values are, in order to get the S parameters that we're seeing. So once this simulation is completed, let me just see, we're getting close. Okay, so it's done. So once this is completed, we can see what are the final component values that are chosen, and then what is the final predicted S parameter range that we would be getting given these component values. As a verification step, now that everything is completed, I can apply these component values to the project. And so if I come in and I look at the value for the inductor, I can see that this value matches up with the predicted value, the selected optimal value. And then I can come in and run another XFdtd simulation and verify that I'm getting the correct results that the optimizer predicted. Instead of running that XFdtd simulation and showing you the results through the UI, I just went ahead and plugged it into the slideshow. So here we optimized on S parameters. The graph is showing the red line is the unmatched antenna, so this is what the impedance would be, or the S parameters would be for the antenna if it was not matched. And then the blue line is showing the S parameters that we would get using the values that were determined by CEO. So again, in the lower band, the GPS band, we're getting better than a -4 dB match, and in the Bluetooth band, we're meeting the -10 dB threshold that we defined. And I had also saved planar field distribution through the active antenna, and here we can see certainly some strong coupling from the antenna onto the ground plane and then onto the matching network. And so the circuit optimizer is able to get the level of accuracy that it is because it is accounting for all of the full wave interactions in and around that matching network. And so the final thing that I want to talk about here is just some advanced uses using tunable components. Tuners allow the matching network to change states, or the tuners can take on different values depending on the state that it's in. So here if we look at the matching network from the LTE example, I've just changed C4 in the left-hand side there to be a tuner instead of a capacitor. And so this is going to allow us to support different things. One of the uses is building one phone that's able to support multiple operators, or we can handle interband carrier aggregation, or we could look at multiple loading configurations. Support for multiple operators means that a mobile phone manufacturer can design one phone and then sell it to multiple operators like Verizon, Sprint, AT&T. And so after the phone's produced, using a software setting, you can say that this phone is going to go to Verizon, and so I'm going to set the state of all the tunable components so that way we're getting the desired match for Verizon. If the phone was going to go to Sprint, well then there would be a different setting for the tuners to support the match that Sprint needs. Currently, this is difficult to do just because of the level of complexity of meeting all the operators' needs with a single matching network. Interband carrier aggregation is also supported with circuit element optimization. Here we have an example of one operator and their desired frequency bands that they would like to operate in. So you could have a tuner that took on 5 different states, so that way you would get a match over these 5 different bands. However, mobile phone designers are moving towards carrier aggregation so they can speed up the amount of data that's being transferred up or down, and so they're going to want to combine 2 bands. For example, they want to combine band 12 and band 4. CEO is able to recognize this, and you can have 4 tuner states here, where one tuner is able to provide the match over the 2 frequency bands that are interested. And then finally is multiple loading configurations. Cell phones have proximity sensors built into it, and so the phone is able to determine whether or not it's in free space or in a hand or next to your head. And depending on those 3 different physical states, there's different loading on the antenna and therefore a different impedance that the matching network needs to match. And so circuit element optimization is able to take these 3 different states as input and then determine what the optimal values should be. So it will provide a different tuner value for each of the 3 states, but then it'll provide a fixed set of inductor and capacitor components that are optimized for the 3 given states. So that covers everything that I wanted to go over today. I hope you have a good understanding of what the circuit element optimizer feature is and how it differs from some of the alternative methods that are out there. I also went over how it fits into the antenna design workflow and some of the buttons that you can find or use within XF. We do have other step-by-step tutorials that are available that actually walk you through the response matrix and circuit optimization in more detail. And I also went over some of the advanced uses of tunable components. At this point, I'd like to open it up for any questions and also provide you our contact information. So if you would like to learn more about this feature or discuss your use case with us in more detail, certainly feel free to call us, and we're interested in talking to you. So thank you for your day and thank you for your time.